First of all, thanks everyone for taking out time on a Friday morning to come to RootConf. Really thrilled to be here and talk about Flipkart's journey on database in Kubernetes. So about me, I work as a SEM in platform engineering side of the world in Flipkart, which means my team takes care of almost all of the databases in Flipkart. And Flipkart has like a really large scale if we talk about the scale aspect. So I won't take too much time and probably get started on this thing. So yes, first question. I think, what do these two images have in common? Left side is Toyota's flagship SUV. It's called Innova Hycross. Right side, I hope you have seen this logo before. If you haven't, I'll be very disappointed. It's called the Big Billion Days, of course. Flipkart flagship event, Big Billion Days. Anyone? I can give you a hint as well. The hint is RootConf itself. RootConf is the hint. All right, so the answer is both are powered by hybrid technology, right? RootConf is also a hybrid event for today, which means there are people who are sitting here. There are also people who are streaming and all of that. But basically, both are powered by hybrid technology. Now, what is this hybrid technology that we're talking about? So this is called the hybrid powertrain, this particular car, as it was recently, in fact, unveiled by Nitin Gadkari as one of the things that India is sort of planning to invest on. This car can run on petrol-ethanol combination as well as battery, right? It's got a flexible petrol to ethanol ratio. What does it mean? You can fill it with 100% petrol if you want to, it'll run. You can have 85% ethanol and just 15% petrol, then also the car will run, right? I mean, of course, you might not get that same performance from the car as you would want, but it runs. You can also use the EV for city, right? And you can use the petrol-ethanol combination for your highway, whenever you're going out on larger highways, right? And it's reasonably protected against fuel price hikes. What do I mean by that is tomorrow if the price of petrol goes up significantly, you can still start switching to ethanol slowly so that your price remains sort of constant. Now hybrid cloud, Big Billion Days is powered by hybrid cloud. This is very similar. This can also run on both two kinds of things, right? It can run on both on-prem as well as public cloud. It's got flexible on-prem to public cloud loads, which means you can decide how much you want to load the on-prem, how much you want to load the public cloud. We typically use on-prem for BAU loads and public cloud for BBD loads. BAU is business as usual. BBD, of course, is Big Billion Days. So the ratio that we have from BAU to BBD is like significantly high. I won't talk about what is that X, but it's a very large X, right? And we are also reasonably protected against public cloud costs. And a lot of you must be using public cloud over here, and we are reasonably protected against this cloud because of this whole thing. What are the key advantages of going hybrid? Number one, I think there is good amount of cost efficiency that comes through. Why? Because there's no need to purchase upfront a lot of hardware for just 1 month of BBD. So typically what used to happen before the hybrid cloud is Flipkart used to purchase a good amount of hardware, keeping in mind the amount of scale required for BBD, and then keep that through the entire year. However, we are not utilizing that to the full potential, which means we are wasting a lot of money, right? So instead, hybrid cloud, what it allows us to do is we go public. I mean, we start using the public cloud just for that 1 month of BBD, but for the rest of the year, we don't invest on additional hardware. So it means a lot of cost for us. Reliability aspect, there's a far better BCP-DR posture. When one cloud goes down, the other is there to sort of save the day. I'm sure you would have also read about recent reports. I mean, even public clouds sort of face these kind of problems. So it's not like your data center goes down, public cloud is there to help. Sometimes even the public cloud goes down and your data center is there to help, right? Both aspects come into picture. Flexibility aspect, we decide when and what goes to on-prem and what goes on public, right? Depending on the kind of workload that we have, we can decide what goes here, what goes there. So finally, the scalability angle, we can burst out into the public cloud. The term used again here is called bursting out. It's like an explosion because sometimes, and it happens sometimes, right, that you sort of predict this kind of load is going to come, but then, well, the offers are so good that, a lot of people want to come and buy phones or whatever they want to buy, and then you're like, what do I do with this kind of, load? Public cloud helps you because it can burst out. Literally, it's called bursting out. So these are the advantages. So now we have established that hybrid is important, hybrid cloud we talk about, but then how do you manage this hybrid cloud? Is it easy? What happens when private cloud meets the public cloud? Any guesses? lightning strikes, that's what happens. So hybrid cloud is needed, but it's not very easy to manage. But managed services, they abstract away a lot of this complexity. And managed public cloud generally don't integrate very well with anything outside the cloud. I'm sure you must be knowing that if you're using a managed service within the cloud, it's not very easy to integrate it with your own services outside the cloud. And there's a good reason for that also, right? They want you to stay within the cloud, any public provider. Public managed services they also can't be installed on your on-prem data center. So if you go and say, hey, I love this Cloud SQL product, or I love RDS, right? Can I take it and put it on my data center? You know what the answer would be, right? They would say, no, that's not going to work, right? So we spoke about hybrid cloud and self-managed. So any ideas, how to solve this problem? Atmanirbhar. Atmanirbhar is basically self-reliance. You would have heard this terminology in the last couple of years. I'm sure this word has been around, so I'm sure all of you are sort of aware of this word, right? So the idea is basically you have your self-managed service on an on-prem talking to, again, your self-managed service on a public cloud. And that's the only way this sort of works really well, the integration between your public and your private in a hybrid cloud setup. So you have a self-managed, little small cloud there and your self-managed service on a big public cloud there. But here only beautiful rainbows can be seen. There are no more lightning that is going to come in this setup. How do you build self-managed hybrid services then, right? Like we are continuing the story, right? Like how do you do that? So we have established that somehow we have to make our services as managed as possible using this hybrid cloud. So enter CNCF. Has anybody over here heard of CNCF? I hope a lot of you have heard. If you haven't heard, okay, we'll talk about it. So the mission statement of CNCF is fostering the growth of cloud-native technologies to create a sustainable ecosystem, right? So basically, this is an organization that is going to support a lot of these cloud-native technologies, and it's a pretty famous logo. Maybe the logo is something that a lot of you have seen. So that's called Cloud Native Computing Foundation, right? Now, there's a reason why that it's not aligned properly. It's to the right side because there's one more missing piece there. That's Kubernetes. Right? So Kubernetes and CNCF are best friends forever, and before anyone else kind of a thing. They have a very special relationship. It's at the heart of CNCF really, right? As a hybrid cloud enabler. Without Kubernetes, maybe you could say a lot of the things that are happening around in the CNCF world are because of Kubernetes and the kind of disruption, I would say, that Kubernetes sort of brought along. And Kubernetes is one of the projects within CNCF. And largely from the hybrid cloud perspective, what does it do? It abstracts out a lot of the cloud-specific APIs for infrastructure provisioning. And it allows you to do easy management, scalability, and all other kinds of operations you want to do. It makes things far more easier. And finally, it's open source, and there's no vendor lock-in. Has anybody over here heard of vendor lock-in? Okay. So vendor lock-in is basically when the vendor, public cloud vendor, it could be database vendor, it could be different kinds of vendors, right? So once you're into the system, it's very difficult to get out, right? Your costs will start going up, but then you realize there's no easy way to come out of it. So that's called vendor lock-in. And they'll try everything possible to ensure that you stay within the cloud and you don't get out of the cloud because now you are their bread and butter, right? So no vendor lock-in here, right? You can go to any cloud. You don't like Cloud A, you can go to Cloud B. You don't like Cloud B, you can go to your on-prem cloud. So somewhere Kubernetes sort of allows you to do that. But when you talk to people, hey, have you done your Kubernetes? They'll say, yes, we have done our Kubernetes, right? But what have they really done? They have moved their stateless components, right? Stateless services, applications, and all of that are nicely sitting on Kubernetes, right? And people are really happy they have done their migrations. But the moment you ask, hey, what about your database? You need your database as well. But they say, oh, database, we have not done Kubernetes. We are not sure. Stateless applications, all of that is fine. So traditionally, Kubernetes was popular with a lot of stateless applications, right? We'll start getting into a little bit of the terminologies from Kubernetes perspective. Replica sets was the name of the construct that was to ensure that a specified number of replicas of a pod template are running at any given time, which basically means if one of the thing goes down, another one comes up with the same exact template, right? And that is what your stateless used to do. Stateful sets is another construct that we're one step ahead of this replica set. as they also have to deal with something called as persistent storage aspect, which means there's also a disk attached to it where you can also store something and all of that. So that's what. They'll also, you can also have stable identifiers to each of these pods. What does that mean? It means that, hey, when you have multiple pods, right, typically when people are using multiple pods, they're using each of them as a read replica, and then, you say you want to take one down. If it was traditional Kubernetes, it'll take any of them down. And then you're like, hey, I didn't want that down, I wanted this down kind of a thing, that you're using one for analytics, another one is serving some kind of workload. So it becomes a little difficult unless you're specifically saying, I want this particular pod down, I don't want that particular pod up, I want this particular pod to scale up, not that kind of a thing, it gets difficult. And if that is not enough, databases were far more complex. There are a lot of other things. There are replication, scaling, there is shard management, failovers, leader elections, and different databases. And I'm not talking about a particular database, but in general, a lot of these databases have a lot of these complex things going on, which are not just about, oh, there's a disk and there is a memory. It's not about that. There's far more that goes on beyond that, which is, again, not very easy to manage. So there are a lot of red flags. We have established that using Kubernetes directly is not a problem. So now we present something called as operators. It's not like I'm presenting, it's been there around for some time. I'm just presenting in this talk, right? So what's an operator, right? Operators are special tools in Kubernetes that help manage complex applications, just like databases that we talked about, by automating a lot of the tasks that we saw in the previous slide. Think of the operator as a robotic operations engineer. But the only difference is this engineer is highly scalable, highly available, and super well trained as far as Kubernetes is concerned. So almost think of it like an engineer who's actually looking at stuff and automatically doing stuff, but just that you can scale. You want 10 DBAs, DBA or operator, right? Boom, you just say, okay, 10 more come up and they start managing, right? So very highly available, one goes down, another one comes up. And you don't have to be sorry waking this guy up at 3 in the morning when something goes down, right? So, because highly available, right? So, operators are also written in Golang, one of my favorite programming languages. Ever since I moved from Java to Golang, I somehow don't look at Java anymore. it's just too much of code. So, there's something called as operator framework, and you can use the operator framework to build your own operators and extend Kubernetes functionalities to do a lot of this complex. So what kind of databases make sense in the Kubernetes world? Wow, it's a lot. So as if the number of database options weren't enough already, now we have also got operators to think about. So I would say that the cloud native and distributed databases makes most sense when you're working with Kubernetes and databases. Most DBs also now have their own official supported operators. Of course, if nothing works, you're free to build your own. It's also quite possible that from a future-proofing perspective, a lot of these companies want to invest specifically on the newer things that they're building. They want to keep Kubernetes in mind and they're building that. They're not really saying, okay, we are also investing a lot in VM side of the world, right? So that's also happening, just to be right? So from a Flipkart perspective, our experience, we have been running HBase, TIDB, and Aerospike loads on Kubernetes. From some time now, from a couple of years now. And that's been working out well for us, and we'll probably talk about that. So and it's basically called the TIDB operator for TIDB and the Aerospike Kubernetes operator, and these are public operators. The HBase one is our own operator. We are also building a MySQL in-house operator. Hopefully we'll also have that probably by next year sometime. Maybe one of my members from my team can also take a talk on the MySQL operator. But then again, can it be that simple, right? Like that's the question, right? Like we spoke about a lot of these things, how operators and the whole story is coming, right? So there's a lot of the things that don't meet the eye, right? Like we all feel, okay, this is all ideal and working, but somehow Kubernetes is in general the orchestration, container orchestration. Right? This is container orchestration. These are actual containers, right? Ship containers, right? It's not very straightforward. The philosophical problems with Kubernetes, right? Pods will be killed whenever they are needed, right? They will just spawn up again. You talk to a Kubernetes infra kind of a thing, right? The philosophy is generally this, right? It can go down anytime, it can come down anytime. Why do you care, right? But boss, we have something called as local attached. There's a disk there. You can't just take down disk and again bring it back up, right? So if you're using something called as a locally attached storage, it changes everything, right? You can't really take it down and bring it back up whenever you feel, you want to do maintenance. You can't take it down, bring it back up. Like who will copy the data? Operator, yes, but right? Upgrades take significantly longer due to this, right? So you're upgrading the entire fleet. Suppose Kubernetes team is there and they want to upgrade the entire fleet. Stateless, boom, done. 1 week done. You know, take down, bring it back up with the latest Debian or whatever you want. Latest Kubernetes done. It's done. Database, the world, they come to us and then say, oh, stateful cluster, let's take it down. We'll say, no, you can't take it down. You'll have to wait. You know, we have to copy the data. We have to do something. So maintenances take longer if you're using something called as local attached storage. Scalability angle. Scaling up vertically is not always possible. It depends, right? It depends on whether the node in which your pod is there, your storage is there, does it have enough space to actually grow? Maybe, may not be. Well, you can't always be very sure about it. And sometimes it even happens that you think you can scale, but by that time somebody else has taken up that space. That also happens, right? So a promise is not a guarantee always. You try to do it, but sometimes it works, sometimes it doesn't work. And sometimes you have to end up doing horizontal, scaling. Horizontal scaling means it's something called as rebalancing happens. The data keeps moving here and there, so that performance implications are there. And if you increase disk alone, you can't increase disk alone. Like database people write I'm running 85, 90% on my data. Just give me some more disk, right? It's possible in a lot of these things, but it's not. In Kubernetes, you have to also increase the cores and memory, especially if you're doing horizontal kind of scaling. So these challenges are there. So I just want to say that Kubernetes is not magic, right? Like people sometimes think Kubernetes is magic, operators are there, boom, everything is working really fine, but they are not. Pods always don't get scheduled. There's something called as bin packing. Has anyone heard of bin packing problem? Bin packing is almost like, I don't know, it's like there's a constrained space and you want to park vehicles there, which vehicle goes there so that you don't have, it's like defragmentation, maybe in that world, right? You can read about it, right? There's something called as maintenance domain. What is maintenance domain? Maintenance domain is when people are doing maintenances, they take down one maintenance domain at a time. So they say that, okay, your workload has to be distributed across maintenance domains. They can't guarantee it again, right? Sometimes two of the same pods fall in the same maintenance domain, and when they take that maintenance domain for maintenance, boom, two of your pods are gone. From a maintenance perspective itself, right? Again, Kubernetes doesn't mean failures don't happen. Bare metal, virtual machine, node level failures still happen, right? Again, the pod keeps getting killed. And whenever, and some pods can be errant also. They can be performing not that great, right? It's not very easy to move out of it. You can't say, I don't want this particular pod, this particular node, but I want that particular node. You can't really control it very easily, right? And even if you say that, and if you move out of it, somebody else might come and sit there. So unless there is also rigor from the hardware team to take out those things which are reporting, so there is a little bit of work around it, which is not straightforward. And planned upgrades keep happening far more frequently than virtual machines. Now you've also got your Kubernetes upgrades, OS upgrades, security upgrades, and all the other things that come with Kubernetes like Istio. Everybody wants to upgrade. So a lot of the time you're just upgrading stuff and then figuring out what's happening with your fleet. Kubernetes alerts, right? I'll talk about the MTL part, telemetry and alerts, right? This can escalate really quickly. So typically, the way we want to think about it is there's a Kubernetes control loop, which I'm hoping a lot of you are aware of it. The first level of auto recovery, if pod goes down, automatically it brings it back up, right? The second thing is the operator. Operator says, so if you can't do it, let me figure it out and let me try to bring up the auto recovery, try to rebalance stuff and all of that. The third thing is you also have a management plane that says, hey, if operator is also not able to do, I will come and fix for you, right? So there are different levels. And then finally, if none of these guys are able to do things, you say, okay, the on-call engineer is expected to solve it. But so what this means is you have to configure your Kubernetes alert policies like really well. If you don't do it, all of the alerts that are happening in step 1 will directly reach step 4, right? So every small thing, even though it is being taken care of by K8s, by operator, by management plane, you will still keep getting a lot of alerts. And this especially becomes like a really big problem if you're managing a very large fleet. You're bombarded with alerts, right? And you don't have to do anything about it. That's the worst part. You don't have to do anything about it. You're like, okay, the operator is taking care of it, but why am I getting the alert, right? So that problem typically comes. Next, we'll talk about Kubernetes storage. You'll have to choose wisely, right? Anyone has any idea what JBOD means? Yeah, it's just a bunch of disks. That's what all it means, JBOD. For a long time, I used to think, oh, JBOD must be some technology, and then somebody said, it's just a bunch of disks. That's what it is, right? So locally attached storage is called LAS, we'll call it LAS. Network attached storage, we'll call it LAS. And there's also elastic block storage, which is EBS. A lot of you must be using EBS in your public workloads. EBS is like network attached storage, but also which can also, you can elastic, like a rubber band it is, right? Local attached storage is, you can't do anything. It's there on your same node, and it's got its own limitations, right? LAS gives you great performance. It's cheaper and has far lower latencies, right? But it doesn't scale up, and it is notorious for not having any kind of failover. There's no failover, right? It's on that node. If that node goes down, okay, bye. Your application, your database has to take care of replication and everything else. If that doesn't take care, then you lose your data. It's simple. Network attached storage gives you better performance. It's over the network. Your disk is over the network. That's all it means, right? It's not on that same motherboard or wherever it's like on the mothership. It's not on the same place. It's separately kept. It gives you slightly lesser performance. It's costlier though, right? And it has network redundancy built in, and it gives you some amount of failover capabilities. So that's what it does. EBS also gives you additional disk level redundancy, basis different kinds of things. Disk level redundancy, if one disk goes down, it automatically also does a failover to the other disk so that you don't really, this thing. And it also allows you to scale up and scale down. Right? Scale down, again, some problems are there. Scale up definitely does. Some places, depending on vendor to vendor, some vendors don't allow you to scale down well. Scale up is generally easily. So those kind of things come up. So be very careful, like what kind of storage you're using. And other thing to take care of course, is your bills, right? Auto scaling and resource utilization, right? The problem that we see is whenever we introduced a lot of these auto scale EBS kind of workloads where people don't have any more roadblocks, right? There are hardly any roadblocks. It's like a 8-lane highway, right? People just go. They don't care. They're like, oh, but the disk is getting full. Add 10 more dabbas. We are fine, right? Like they don't care. MySQL, they're like, oh, you're reaching 80%. And we are like, you have to start archiving your data. People are serious about it. Now they're like, oh, no, add a couple of more. It's fine. There's no failover. There's nothing. There's no switchover. There's no DNS. Nothing. You just keep adding, right? So when you don't do it, it's very, very easy to overuse some of these things, right? Especially auto scale and these kind of constructs. Resource limits is another thing which really helps with noisy neighbor and planned resource usage. If your neighbors don't have good resource utilization limits, right, they will end up eating your food. There's common food, and if they are eating your food, it becomes very difficult, right? Then you are like, hey, I was supposed to get, some 2 rotis. I'm only getting 1 roti. Why? Because somebody else ate your food. So it's important that everybody on Kubernetes, on your stateful stack, all these services, everybody is using resource limits so that they don't really, eat up somebody else's thing. And sometimes not every resource, for example, is limited. For example, network. Sometimes if it's not limited, somebody else might eat up all your network. And they'll say, oh, you got your disk and your, what's the problem? But network also is important, right, sometimes. And there's also this concept of on-demand, reserved, spot instances. So, when you're choosing these things, understand what these things are and don't generally go for the highest tier. You also need to think about the backup cost. What is the incremental versus full? Every time if you keep taking full, it might bloat up your backup and your the storage that you're using, those kind of things. And billing, it's very easy for resource leakages, especially with a lot of disk, right? Sometimes disk, especially when disk is there, you forget about it that, okay, there is one node. And I'm sure a lot of people who are using public cloud will be able to identify with this. You spawn up something, and then you forget about it, and one fine day at the end of the month, they'll say, okay, boss, you're supposed to pay these many dollars, and you're like, oh, was it still running, right? So you have to be really careful about these kind of things. Ensure that orphan data which nobody is using, is cleaned up regularly. So next we talk about Kubernetes performance versus cost versus availability. And this is largely the thing that you'll also have to evaluate whether it works for you or not, right? Flipkart's primary comparison, at least, right, was always with respect to virtual machines, right? We were not really, a lot of you might be thinking from a public cloud perspective, but our perspective was largely from a VM perspective. So in an apple-to-apple comparison, if you were to think, VMs are generally far more performant than Kubernetes, right? How much? It depends. There's no answer. I can't say 5, 6, 7, or whatever, right? Or 100. I can't say any number like that. It really depends on the kind of workload you have and all of that. You'll have to do your benchmarking and then figure out what makes sense. Kubernetes has better availability than your virtual machines because of the HA operator. I know VM also has availability kind of a thing where you say, oh, I have a primary, I have a secondary, and the primary fails, and then this gets promoted and all of that. You can do all of that. I'm not saying you can't do, but Kubernetes generally has these constructs built in natively, right? Kubernetes also can be installed directly on bare metal or again on a virtual machine, and different kinds of disk flavors are there. So all of this sort of affects the whole performance angle, right? So when people come, they should not be thinking that, hey, in virtual machine with this core, I'm getting this performance, with the same number of core, I'm not getting performance, right? So that's not the point, because you're also getting something more here, which means the additional dollar that you're paying is the hardware cost you're paying, or for getting higher availability for the same or better performance also, right? So if you look at it that way, you don't do 10 cores, you don't do, maybe 10, maybe this is 12, right? But you're also getting something better than that. Yep. And then finally, I think staying relevant. Kubernetes is also future-proofing in some way. Tons of innovations that are happening in the Kubernetes world. A lot of new technologies are increasingly being focused in the Kubernetes world, right? So staying back in VM might also mean that you are sort of losing out on a lot of these innovations which are happening. In fact, if you look at the CNCF page, that page itself, right, it's very hard to comprehend the number of startups, the number of products, the number of things that have come up, mushroomed literally right in the last couple of years. So moving to K8s, at least I would think it would reasonably future-proof you. If you're not going there, then some problem, there could be some problem, right? And like I already mentioned, it's quite possible that future versions of databases might be exclusively built keeping Kubernetes in mind. So you'll have to evaluate the scale, availability, reliability of your business, and you'll have to, so don't just go to Kubernetes because I'm saying it, but then you'll have to evaluate what makes sense for your organization, because these are dependent on what makes sense for your organization. Now, very quickly, we'll start looking at some of the practical examples. So we use TIDB operator. TIDB is the, has anyone over here heard of TIDB? So some of you have definitely heard. Okay, so TIDB is the scalable MySQL compatible distributed store. Flipkart uses this to power its MySQL workloads, right? So the ones which are not really working out on a VM, on a single node kind of a thing, we try to put them on TIDB, because these are a little bit far more scalable than compared to the VM MySQL thing. So how do you deploy the operator? Use Helm, and Helm installs the operator on Kubernetes. It's pretty much that. That's pretty much it. Various ways to do it. Again, depending on your organization, might be using various things. As soon as you do this, your operator pods are sort of running, and then they are waiting for instruction, right? Instruction is what your CRDs or whatever I can call it, right? And it's just waiting for, okay, tell me what to do, right? So that's what it is doing. Expected time, this is like really quick, few minutes after that, and you're sort of done. Now, next thing is we'll deploy a new TIDB cluster using the operator, right? So now, this is your Kubernetes world, and there's that, the Kubernetes that controller and all of that, and your operator is now sitting there nicely. So the user comes and then he creates a CRD. So CRD is nothing but like sort of telling what you want that operator to do. It's like giving it's like a UI for this thing, right? In some way, like what you want, you're giving an instruction to what you want to do. So this guy watches that, and anytime any change happens there, he listens to that and then adjusts the state with Kubernetes, which makes the changes and then creates the pods. Right? So we have got some stateful sets, some PVs, and some pods, and all of that created depending on what is it that you have sort of specified. So very straightforward. And this whole thing becomes your database, right? Of course, you'll have a load balancer on top of it, some service endpoint, and all of that. So eventually, a combination of all of this. For example, in TIDB, there are various components. It's not just one pod. There are various components which make up the TIDB database. So a lot of these get created, and then it's ready to serve of sort, and you can basically connect to it. This is how it typically works. Expected time, again, very few minutes for empty cluster. Of course, if you want to copy data, it will take a lot of time. The next one we'll talk about is vertically scaling up stateless components using operator. So TIDB also has some stateless components. It has stateful components also. So what do you do? Again, you put the CRD. It watches the CRD. I'm not going to talk about the same thing. It's the same thing, right? You see the same thing happening, and then it goes up and it makes your pods bigger, stateless components. Again, in a few minutes, all of that is possible. How do you horizontally scale up the stateless components? Again, same stuff. It just creates more pods, right? And you have scaled up in a different way, right? Again, few minutes it takes. Now we'll talk about stateful components, right? Using operator. The same thing, you apply a CRD, watches, change events, adjust state, makes changes. Now you see there is a pod here and there's a PV there, which means the disk is attached there. It just makes both of them bigger, right? So that's how you vertically scale up. Like I also said, it's not always that vertically scaling is possible. Sometimes it's possible, sometimes it's not possible. So if you're using network attached storage, it's far more easier. Or in specific local attached storage situation, it might even take a lot of time because when the new PV comes up, it might not come up on the same node. It might need to come up on an entirely different node, which means who is going to copy the data? If it's like a TB of data, that TB of data needs to be copied all the way there. So it depends. If the node on which your pod was there, if it has headroom for growth, only then this is possible. If not, it will take a lot of time. So you'll have to evaluate. Like, don't give your customers saying, 2 minutes, I'll vertically scale it up, and then you boom, you're done. You give the command, and it takes like 3 hours, 4 hours, and that guy's like, you told me it's like 2 hours, right? 2 minutes, and it's now taking 2 hours. So it depends. Evaluate whether that node actually has that capability to grow. If yes, then you can do this. Horizontally scaling up stateful components using operator. So first, the rebalance happens. It creates the pods. And then the rebalancing is happening. Once the rebalance happens, you have got one more this thing, right? A pod and a PV attached. So it depends. The time it takes several hours. It could depend depending on the data size. Now, failure management, let's say, like network attached storage, as in only the compute is failing, but the disk is still there, right? Local attached storage both fails, right? We'll talk about that later. But network attached storage means only your compute has failed. Storage is still happy, right? So this guy is also watching these native resources. So there's no command that has to be given now, right? It's a failure, which means it's unplanned. Nobody knows about it. Night 3 o'clock, this is happening. Suddenly, this pod has gone down. This compute has gone down. But the PV is still there. Your data is still there. So that is good. So it adjusts the state and then makes changes. A new pod comes up, right? A new compute pod comes up, which attaches itself to the PV, and then you are sort of done. So few minutes again. Hardly takes time. Failure management is local attached storage. Local attached storage, like we talked about, both of them fail. Disk also gone and your pod is also gone. Of course, there are more of these things there, right? And just for brevity, I've just put one pod and one PB, but there are probably more of such things, right? Because a distributed database, it is copying data. This is not MySQL single kind of a thing. If you're on MySQL and you're doing this, you can close your shop and go back home, right? But this is not MySQL. This is a distributed SQL. Both are gone now. This adjusts the state, makes changes. First a pod comes up, PV is empty because there's no data there. The data has to be copied. It will take quite some time. It has to figure out where all regions, where I have to copy and all of that. After all of that copying is done, it also becomes blue in color, ready to sort of serve traffic. And then we remove the ones which are not sort of working. And if you don't forget to remove them, it is going to add up to your bill, right? Several hours depending on the data size. Triggering a backup using an operator. And these are all common things that people do with databases. That's why I'm covering a lot of these things. You create something called as a backup CRD now. CRD, again, the language, right? Like what you're instructing it. It watches, changes events, adjusts the state, makes changes, creates a job now, right? And that job basically creates one more big pod and a big PV because you have to take the backup. And again, taking the backup and that gets filled up. Once that is done, it starts uploading it to some sort of cloud, your GCS or your S3 or wherever, right? And then deletes those things. So you're sort of again done. We also built something called as Flipkart also, we built our own operator to handle some more things which these operators weren't doing. That's called schedule maintenance operator. So basically, again, if hardware issues are detected in our own on-prem, the Kubernetes team sort of informs us saying, hey, they used to inform by email, hey, oh, this node is going down, and they wouldn't do it even for stateless, saying, oh, your pod will come somewhere, why to even tell people, right? But for us, they had to tell, saying, hey, it's going down, do something about it. So we used to actually remove them from that node and then plant it on some other node which is not going to have that maintenance and all of that. And it was very error prone because my engineers had to keep seeing that email saying, oh, the email has come. Almost done, yeah. So now what they do is they just create this CRD. right? Schedule, maintenance, CRD, and rest everything is automated. Now you see there's also a small operator there. That is our operator. There's also the big operator, which is the TIDB operator, and there's the Flipkart operator. So what happens is, again, that CRD comes here. This small guy watches that. Big guy is not watching it. The small operator is watching it. He changes events and works with that guy, adjusts the state here, and then creates two new ones here, right? So basically these are the ones which are going for maintenance. The orange ones are going for maintenance. So we create two additional ones, two additional pods we create, again empty PVs. After some time, those are basically filled up. And then we remove the ones which are going to die maybe after a day or so, right? So we have moved out of the problematic sort of node. And moved out of it, when you kill it, again the new ones come back up. Kubernetes, that's what happens, right? The new pod comes and the new PV comes. That PV again gets, data gets copied over. So now you have got two extra. Then you delete those two extra. So you have sort of done it in a way that you are safely sort of doing it. So this is a planned maintenance. Unplanned maintenance is a different story. So we can tolerate, for example, one unplanned maintenance, but during that unplanned maintenance, if one more unplanned maintenance happens, then again, it's a big problem, right? So yeah, that's pretty much it. I want to sort of wrap up the talk. End of the day, it has to make sense for your business. And thanks a lot for this thing. Yeah, I'll probably take questions now. Yeah.
So for distributed DBs, like you can probably think of having something on-prem and the public cloud, but there will be like some kind of latency between the write, read, replicas, etc. If you're hosted like on a poly cloud kind of a thing, right? But for DBs like Postgres, MongoDB, etc. So how do you get away from the cloud storage itself? Like for example, if it is on EBS and if my client wants to move to on-prem, it's a lot of headache to migrate that data from EBS to something on the on-prem disk, right?
Yeah.
So and like tools like Velero, etc. They also just use the provider APIs that you can use something with RESTIC, etc. Or you have to like spin up a socket and do rsync. So that is like the problem. I was thinking, like, how do you have like a cloud agnostic storage itself? So a layer on top of it is fine, but the storage itself, the network itself, if someone is using like a global accelerator, right, the network itself, how do you make it like cloud agnostic, right? And how do you switch between your like on-prem cloud and where you're basically you have data residing on a public cloud? How do you mentioned that you can switch traffic, right? So how do you move that state from there to your on-prem?
Okay, so the whole movement between, maybe you're probably talking about that if I understood your question right, how do you actually make that movement? There is some data sitting on your on-prem and there is some data sitting on your cloud, and then you want to figure out what goes where and all of that, right? This, again, typically easier with stateless applications, right? Because new things sort of come up there. Stateful applications, you have to be prepared to some extent because you can't do this data copying on demand. Suddenly, if the load comes up there, you can't at that time start copying the data. So you need to still have you need to have a presence in both the clouds at all times. Replication is going on, so you're not really copying. So it's not really that the disk is abstracted out completely across this thing, because the disk also is very, very different, right? Is what you realize, the kind of purchases you're doing for your on-prem and the kind of purchases you're doing for your public cloud, the costs, everything is very different. Performance, everything is different. So you can't really abstract it out at that level. But then you'll need to have your presence in the public cloud at all times, so that if you want to, burst out into it, it's more easier, and you don't have to start copying data from this data center to that over the network at peak time.
You kind of have regular
yes.
And put it on object store.
Yeah, not object store, but yeah, maybe.
Okay. Thank you, Vaidyanathan.